On the morning of August 24th, 2016, a small group of astronomers stood in front of a room of reporters in Munich and said something that made the closest star to our own sun suddenly worth caring about. Guillaume Anglada Escudé from Queen Mary University of London had spent months running a campaign he'd named the Pale Red Dot, watching one faint star for the smallest possible wobble. 24th, what he found was a planet, roughly the size of Earth, and orbiting inside the habitable zone, close enough that liquid water could, in principle, survive on its surface. For a few days, that was the whole story, and it was a good one. But the habitable zone is not a promise. It's a distance. It only says a planet is close enough to its star to be warm enough for water. If nothing else has gone wrong, something else had gone wrong. 24. This is the story of what that something was and why, on 3 worlds circling our nearest neighboring stars, it may already be over before it began. Alpha Centauri has been in our sky for as long as there have been eyes to look up. It's the 3rd brightest star system visible from Earth, low in the southern sky, and for most of human history, it was just a point of light like any other. What changed in the last century is that we learned it isn't one star. It's 3. The 2 brightest, Alpha Centauri A and Alpha Centauri B, orbit each other closely enough that early telescopes could barely separate them. Both are what astronomers call sun-like. A is a G-type star, slightly larger and hotter than our own sun. B, a K-type star, a little smaller and cooler. If you'd grown up under either one, the sky would have looked almost the way it looks here. Warm light, a familiar color, a star doing more or less what our star does. The 3rd member of the system is different in almost every way. Proxima Centauri is a red dwarf, small, dim, and much fainter than its 2 companions, orbiting them both from a vast distance, so far out that it takes hundreds of thousands of years to complete one loop around the pair. It's called Proxima because it happens to be slightly closer to us than the other 2, a difference of about 1/10 of a light year, which in practical terms means nothing at all. But the name stuck, and so did the attention. When astronomers went looking for planets in this system, Proxima is where they found one first. That discovery, the one announced in Munich in 2016, came out of a very particular kind of patience. For years, researchers at the European Southern Observatory had noticed something odd in their data on Proxima Centauri. Tiny, regular shifts in the star's light that didn't match anything caused by flares or ordinary stellar behavior. Anglada Escudé's team built an entire observing campaign around chasing that anomaly down, coordinating telescopes on different continents to watch the same star night after night for months. The instrument doing the heavy lifting was called HARPS, the High Accuracy Radial Velocity Planet Search, built to catch a star's almost imperceptible wobble as an orbiting planet tugs on it. In human terms, they were trying to detect a shove so small it barely counts as a shove at all, and they found one. The planet they confirmed was named plainly Proxima Centauri B, slightly more massive than Earth, orbiting close to its star, and, critically, sitting inside the zone where the math says water should be able to stay liquid. It's worth being honest about why that mattered so much, because the reaction wasn't really about the planet itself. It was about what the planet implied. Earth is the only place we know of where life exists. Every other rock and gas giant we've ever studied, in our own solar system and beyond it, has come up empty. So when a world turns up in the habitable zone of the nearest star to our own, it's natural for that single fact to carry enormous weight. Not proof of anything, but permission to hope. And for a while, the hope was reasonable. The habitable zone isn't an arbitrary label. It's calculated from real physics, the balance between how much energy a planet receives from its star and how far away it needs to be for that energy to leave water, neither frozen solid nor boiled away. Every planet we currently consider a serious candidate for life sits inside that zone, including Earth. Being in it is necessary, it's just not sufficient. What the announcement didn't include, because nobody knew it yet, was the deeper history of the star this planet was orbiting. Proxima Centauri hadn't always been the quiet, dim companion we see through a telescope today. It had a past, and parts of that past were violent enough to undo whatever advantage the habitable zone seemed to offer. That's really what this is about. Not one bad piece of luck, but several, layered on top of each other, each independently capable of stripping a world of its chance. The story of Alpha Centauri's planets isn't a story about whether they're in the right place. By the numbers, some of them clearly are. It's a story about everything else that has to go right, and about a system where, again and again, it didn't. We'll start with the star at the center of the first discovery, because its history is the clearest place to see how a promising address can still end in an empty house. Before we get to what went wrong, it's worth sitting for a moment with what these three stars actually are, because the differences between them turn out to matter more than almost anything else in the story. Alpha Centauri A is the brightest of the three and the closest in character to our own sun. It's a G2 type star, about 10% more massive than the sun and around 1.5 times as luminous. If you lined it up next to our sun, you'd have a hard time telling them apart just by looking. Same color, same general size, same basic behavior. It's the kind of star that, on paper, is exactly what you'd want to find if you were searching for a second Earth. Stable, long-lived, not prone to violent outbursts. Alpha Centauri B is its close companion, a K-type star, a little smaller and cooler, about 90% the mass of the sun and roughly half as bright. K-type stars have their own reputation among people who study habitability. They burn a little cooler and a little slower than G-type stars like the sun, which means their habitable zones tend to stay put for a very long time. Some researchers consider K-type stars to be, if anything, slightly better odds than stars exactly like ours, simply because they offer more stable time for something to happen. And then there's Proxima, small, dim, red. A red dwarf, the most common type of star in the galaxy by a wide margin, making up something like 70% of all stars the Milky Way contains. Proxima is only about 12% the mass of the sun, and it emits less than 1% of the sun's light. Everything about it is a smaller, dimmer, cooler version of what we're used to. On the surface, this looks like 3 separate rolls of the dice. 3 different stars, 3 different sets of conditions, 3 independent chances for a planet to end up somewhere survivable. And in a sense, that's exactly right. It's part of why this system has drawn so much scientific attention over the decades. Most stars in the galaxy don't come in threes. Having 3 genuinely different stellar environments this close to each other, this close to us, is unusual, and it means we get to ask the habitability question 3 separate times instead of once. That's the hope, plainly stated. A sun-like star, a cooler, steadier companion, and a dim red dwarf that, despite everything, still manages to keep a planet warm enough for liquid water, simply because that planet orbits close enough to make up the difference. Each of these three paths turns out to run into its own separate obstacle. Proxima's planet inherited a violent stellar childhood, Alpha Centauri. A and B, for all their calm and familiar temperaments, inherited something else entirely: the physics of being locked in a gravitational dance with each other. A dance that makes the ordinary process of building a planet far harder than it is around a single solitary star like our own. We'll get to both, but it's worth pausing on the shape of this problem before we go further, because it says something about how the universe tends to work. Good conditions, in one respect, rarely arrive alone. A star that behaves gently might sit in a system that tears its planets apart before they can finish forming. A star that sits calmly, undisturbed by any orbital companion, might be one that never stopped raging in its youth. Habitability isn't one gate to pass through. It's a long hallway of them, and a world only needs to fail at one to end up empty. If you found your way to this channel before, and this is the kind of thing you fall asleep to, welcome back. And if this is your first time here, somewhere between the physics and the history of how we've learned any of this, if you find it worth your time, the subscribe button costs nothing and helps more than you'd expect. That's the only place I'll mention it tonight. So let's go back to where the story actually starts. Not with the discovery in 2016, but tens of millions of years before it, when Proxima Centauri was a very different star than the one we see today, and the planet that would one day carry its name was already in trouble. To understand what happened to Proxima Centauri b, you have to stop thinking of Proxima Centauri as the star it is now, and start thinking of it as the star it used to be. Every star spends its early life differently than its later life. Our own sun was brighter and more erratic in its youth than it is today, though not dramatically so. Red dwarfs like Proxima are a different case entirely. Stars this small take an extraordinarily long time to settle down. When Proxima was young, something like 10 million years old, a blink of an eye in stellar terms, it was roughly 10 times more luminous than it is now. Not slightly brighter. 10 times. That number is worth sitting with because it changes everything about what the habitable zone meant at that point in the star's life. The habitable zone isn't fixed in space. It's defined by how much energy a star puts out. So it moves as the star's brightness changes. A star that's 10 times brighter has a habitable zone that sits much farther out, which means that the orbit Proxima b occupies today, the orbit that puts it in the habitable zone now, was nowhere near the habitable zone back then. It was inside it. Well inside it. Too close. Too hot. For far too long. There's a specific term for what that does to a planet. A runaway greenhouse state. It's the same basic process that made Venus the way it is, though the mechanism at Proxima happened for a different reason and at a much younger age. If a planet forms with water and finds itself absorbing more energy than it can radiate away, the water doesn't stay liquid. It evaporates into the atmosphere as vapor. Water vapor is itself a greenhouse gas, so as more of it enters the atmosphere, the planet traps even more heat, which evaporates more water, and the cycle accelerates rather than settles. Eventually, the ocean isn't a liquid feature on the surface anymore. It's steam, high in the atmosphere, exposed directly to the star's ultraviolet light. That exposure is the part that matters most. Once water is broken down into hydrogen and oxygen high in a planet's atmosphere. Hydrogen, being the lightest element there is, can simply escape into space. It doesn't need much encouragement. It just needs time and radiation. And a young, overactive star like Proxima was providing plenty of both. Researchers who've modeled this, most notably a team led by Ignacy Ribas, in a set of papers published in 2016, estimate that this vulnerable period at Proxima B's position lasted somewhere between 90 and 200 million years. Not a moment, not a bad afternoon. The better part of 200 million years spent in conditions hostile to the very thing that makes a planet habitable in the first place. I remember the first time I actually did the arithmetic on that number, matched it up against how old the Earth's own oceans are believed to be. Roughly 4 billion years, stable and mostly unchanged for most of that span. It's not a comfortable comparison. Proxima b didn't get a bad decade or a bad millennium. If it had water to begin with, it may have spent a span of time longer than most of the eras separating the first complex cells from us, losing it before its star had even settled into the version of itself we observe today. This is where the promise of the habitable zone starts to run into the limits of what that phrase can actually tell you. The habitable zone describes where a planet sits right now. It says nothing about where that same planet star used to sit in the sky of possibility, decades or eons earlier, before the star had cooled into whatever we happen to be looking at when we point a telescope at it. Proxima b's habitable zone address is real. It's also almost beside the point, because long before anyone could have stood on its surface to enjoy it, the neighborhood itself may already have taken everything that made it worth living in. If a planet loses its water before its star has even reached maturity, the natural next question is, how much? Not as an abstract idea, but as an actual quantity. Oceans, or fractions of oceans, or something closer to none at all. This is where the science gets genuinely difficult, and where honesty about uncertainty matters more than confidence. Researchers measure this kind of water loss in a unit that sounds almost casual for something this consequential: an Earth ocean, abbreviated EOH, meaning the amount of hydrogen equivalent to one full Earth ocean's worth of water. It's a useful unit precisely because it lets you compare a planet's fate to something we can picture. Not molecules, not joules, an ocean, gone or not gone. Ribas and his colleagues, working through the mechanics of Proxima b's early runaway greenhouse phase, arrived at a range for how much water the planet might have lost during that violent youth, anywhere from under a full Earth ocean up to several oceans, depending on assumptions about how much water the planet started with and how efficiently hydrogen escaped into space. A later analysis, led by Ethan Barnes in 2017, using slightly different assumptions about the young star's brightness, pushed that estimate higher still into the range of 3 to 10 Earth oceans lost. 10 oceans from a planet that, if it had them at all, may never have gotten the chance to keep even one. The honest scientific position here is that we don't know precisely how much water Proxima b started with, so we can't say with certainty how much it lost, or whether anything survived the process at all. This is a real, acknowledged gap in what we understand, not a detail being smoothed over for the sake of a clean story. Different research teams, using different assumptions, arrive at different numbers, and the range between those numbers, from less than 1 ocean to 10, is wide enough that it changes the entire character of the planet depending on where the truth actually falls. What isn't uncertain is the mechanism itself, and what it implies for a world that's otherwise sitting in exactly the right place. Imagine, for a moment, standing on a world where the water isn't gradually receding at the edges of a lake, the way a drought works here. Imagine an entire ocean lifted skyward as vapor, held there by trapped heat, slowly torn apart by ultraviolet light into pieces small enough to simply drift off the top of the atmosphere and never come back. Not evaporation as we know it, something closer to a slow, complete unmaking, spread across tens of millions of years, finishing long before anything capable of noticing it could have existed to watch. I've read the Rebus paper more times than I can easily count, and there's a particular sentence in it, almost clinical in tone, describing the planet's early orbit as sitting interior to the habitable zone during this period. Interior to the habitable zone. 4 plain words, and what they're quietly saying is that the planet spent its formative window on the wrong side of a line that would later become the entire reason anyone got excited about it in the first place. The first time I understood what those 4 words actually meant for the timeline involved, I had to stop reading for a minute. Not because the physics was hard, because the timing was so unforgiving. There's a version of this story where none of it matters, where Proxima b formed farther out in the system, beyond what's sometimes called the ice line, accumulated a deep reserve of water ice the way some of the icy moons in our own solar system did, and then migrated inward to its current orbit only after the star had calmed down. In that version, the planet could have arrived at its present position already carrying more water than it needed, enough that even losing several oceans worth during a violent youth would still leave something behind. Some models allow for exactly this possibility. It hasn't been ruled out. It also hasn't been confirmed, and there's no way, with our current instruments, to look at Proxima b directly and check. So the fair way to leave this is where the actual research leaves it. Uncertain, but not neutral. The default case, the planet forming close to its current orbit and inheriting whatever water it started with in that position, points toward a world that lost most or all of it before the star had even finished growing up. The more forgiving case requires a specific formation history we can't yet confirm. What we can say with more confidence is what happened next, because Proxima Centauri didn't calm down and stay calm. The runaway greenhouse phase was only the beginning of what this particular star would put its planet through. It was violent when it was young. It has stayed violent since. It's worth pausing here, before moving forward, to be precise about what kind of claim is actually being made, because the planet lost its water, and the planet definitely has no water, are not the same statement, and this channel has no interest in blurring that difference for the sake of a cleaner ending. What the models show is a strong likelihood, built from physics we understand well, applied to a star whose early brightness we can measure with reasonable confidence by comparing it to other red dwarfs of known age. The uncertainty isn't in whether the mechanism is real. Runaway greenhouse states and the atmospheric escape that follows them are well-established physics, observed in our own solar system on Venus and modeled extensively elsewhere. The uncertainty is in the starting conditions, how much water Proxima b had to lose in the first place, and whether all of it went, or only most, or only some. For context, Earth's own atmosphere holds a vanishingly small amount of water vapor at any given time compared to what sits in the oceans below it. If you took all the water vapor currently in Earth's sky and somehow lost it entirely, you'd barely notice from orbit. The oceans would remain. What happened to Proxima b, in the scenario the evidence points toward, is closer to the reverse. The entire ocean itself, not just the vapor above it, spent millions of years functioning as vapor, permanently exposed to the process that destroys it. This is where a domesticated number helps more than a precise one. 10 Earth oceans, the upper estimate from the Barnes 2017 analysis, doesn't mean the planet had 10 times as much water as Earth to spare. It's a measure of total hydrogen loss over the whole violent period, compounded across tens of millions of years, one Earth ocean's worth of hydrogen at a time. Even the lower estimate, under a single Earth ocean, would be catastrophic for a small rocky planet that likely started with something in the same general range Earth did. None of this means we can say, with certainty, that Proxima b is bone dry today. What we can say is that the physics driving the loss was real, sustained, and specifically tied to conditions that only existed because the star was so young and so bright. A slower, cooler start would have spared the planet most of this. Proxima didn't offer a slower, cooler start. It offered 10 times its current brightness, for the better part of 200 million years, at exactly the distance where Proxima b happened to be sitting. There is one scenario that keeps the door open, and it deserves to be stated plainly rather than dismissed. If the planet originally formed farther from the star, beyond the point where ice can exist in solid form, even close to a young star's heat, then migrated inward only after the worst of the youthful brightness had faded, it could have arrived at its current orbit, already holding a reservoir deep enough to survive significant losses and still retain something. This isn't a fringe idea. Serious modeling teams treat it as a live possibility, not a rescue fantasy invented to soften bad news. But it requires a specific sequence of events that we cannot currently verify from 4 light-years away. No instrument we have today can look at Proxima b and measure whether it has an ocean, an atmosphere, or neither. We're reasoning from physics and probability, not from direct observation. That's an honest limitation, and it's one that will likely persist for a long time, possibly decades, before any mission or telescope changes it. So here is where the evidence actually leaves us, stated as plainly as the data allows. Proxima Centauri b almost certainly experienced a water loss event, severe enough to strip most or all of an Earth-sized ocean from its surface, sometime in its first 200 million years of existence. Whether anything survived that event depends on a formation history we cannot currently confirm. That's the state of the science. Not a verdict delivered with total confidence, but not an open question either. A likelihood strong enough to shape everything else this planet would go on to experience, and weak enough in its remaining uncertainty to leave a narrow door not quite closed. We'll come back to that door later, once we have covered everything else working against it. Because the water wasn't the only thing this star ever threatened to take. Let's stay with that narrow door for a moment, because it's the most honest place to end this part of the story, and because what comes after depends on understanding exactly how narrow it really is. 2 research teams working through what's sometimes called the LMD Generic Global Climate Model, a tool originally developed to study Earth's own atmosphere and later adapted for other planets, have tried to map out what Proxima b's climate could look like under different assumptions about how much water survived. Their conclusion isn't a single answer. It's a set of branches, each one depending on a variable we can't currently measure. In one branch, the planet retained enough water to behave as what researchers call an aquaplanet, a world where water is abundant enough to flow and circulate the way it does on Earth, redistributing heat between the permanently sunlit and permanently dark sides that come with an orbit this close to its star. In that branch, the ocean itself becomes a kind of thermostat, carrying warmth from the day side toward the night side, potentially keeping large stretches of the planet within a survivable range despite the extremity of its orbit. In another branch, most of the water is gone, and what's left is a planet with a thin, dry atmosphere, unable to move heat efficiently, leaving one side scorched under a star that never sets, and the other locked in permanent cold. In this branch, if anything resembling liquid water exists at all, it would only be found in a narrow strip, the terminator, the line separating perpetual day from perpetual night, where temperatures might sit somewhere survivable simply because the sunlight there arrives at a grazing angle rather than straight overhead. Both of these are legitimate scientific scenarios, built from the same underlying physics, diverging only because the one number that would settle the question, how much water actually survived the runaway greenhouse phase, is a number we don't have. I want to be careful here, not to let the more hopeful branch do more work than it's earned. It's tempting in a story like this to end this section on the optimistic possibility, because it's the version that lets a listener drift off, feeling like there's still a chance. But that would be dishonest about where the actual weight of the evidence sits. The default case, the one that requires no special formation history, no lucky migration from farther out in the system, is the dry one. The aquaplanet scenario is possible. It isn't the planet's most likely inheritance. What's genuinely true and worth holding on to without inflating it is that we don't know for certain. Nobody does. Not the researchers who ran these models, not the team that first found the planet in 2016, not anyone currently working in this field. The uncertainty here isn't a gap waiting to be politely filled in with hope. It's a real, structural limit of what can be known about a world 4 light years away, using only the tools we currently have. This matters for how we think about the rest of this story too. Everything that comes next, the flares, the radiation, the tidal locking, all of it happens on top of whatever water situation the planet ended up with after its first 200 million years. If the planet started dry, these later events are largely irrelevant. There's nothing left for them to strip away. If the planet somehow retained a deep reservoir, then what happens next becomes the more important question. Does an ongoing active red dwarf finish what the runaway greenhouse phase started? Or does the planet's water actually help protect it from what comes later? We're not going to resolve that question in this section, because it can't be resolved yet by anyone, on any channel, using any data currently available. What we can do is follow the physics forward, honestly, and see what a modern, mature Proxima Centauri does to a planet in this position. Water or no water. Because whatever this star did to its planet in its youth was only the opening chapter. It never really calmed down. Most stars, once they settle into what astronomers call the main sequence, the long stable middle period of a star's life, become fairly predictable. Not unchanging, but calm in the way a wide, slow river is calm. our sun still produces flares and eruptions. But they're the exception, not the rule, and Earth's magnetic field and atmosphere absorb most of what reaches us without incident. Proxima Centauri never really made that transition into calm. The reason has to do with something happening deep inside the star, in a layer astronomers call the convective zone. In a star like our Sun, energy moves outward from the core in two different ways, depending on how far from the center you are. Through radiation in the inner layers, where photons slowly bounce their way outward, and through convection closer to the surface, where hot plasma physically rises and cooler plasma sinks. The same basic process that makes a pot of boiling water churn. This layered structure matters because it creates a kind of internal shear, different layers rotating at slightly different rates, which is part of what generates a star's magnetic field in an orderly, gradually cycling way. Proxima Centauri doesn't have that layered structure. It's a fully convective star, meaning the churning process extends all the way from its surface down to its core, with no calm radiative layer in between. The entire star is in constant motion, top to bottom, and that motion twists and tangles its magnetic field far more violently and unpredictably than happens inside a star like the Sun. Eventually, that tangled magnetic field reaches a point where it can't hold together anymore. It snaps, reconnects, and releases a burst of energy across the electromagnetic spectrum, in visible light, in ultraviolet, in X-rays, sometimes even in radio and millimeter wavelengths. That burst is what we call a flare, and for a star like Proxima, it isn't a rare event. It's routine. Meredith McGregor, an astronomer at Johns Hopkins University, who has spent years studying Proxima's flare activity across multiple wavelengths, put the comparison plainly in describing why this matters so much more for Proxima than it does for us. Our own Sun's activity doesn't strip Earth's atmosphere away, because Earth has a thick atmosphere and a strong magnetic field standing in the way. What Proxima produces, by contrast, is powerful enough that a planet without those same protections would have no such luck. In human terms, think of it this way. Standing outside during a thunderstorm on Earth is uncomfortable but survivable, because you have shelter to retreat to and skin and clothing built to handle rain and wind. What Proxima subjects its inner planet to isn't rain and wind. It's closer to standing directly in the storm's lightning strike zone, over and over, for the planet's entire existence, with whatever shelter the planet managed to build for itself, if any, being the only thing standing between the surface and the star. And these flares aren't small. They're frequent enough and violent enough that in 2024 astronomers, using the Atacama Large Millimeter / Submillimeter Array, working specifically to characterize this activity in the millimeter wavelength range for the first time, described their results as doing nothing to ease concerns about whether systems like this can support life at all. That's a careful, understated way for a research paper to put it. The data didn't offer new hope. It confirmed the pattern. What makes this especially relevant to Proxima b specifically, as opposed to being a general fact about the star, is the planet's distance. Proxima b orbits its star once every 11.2 days, at a distance of only about 5% of the distance between Earth and the Sun. That's extraordinarily close, closer than Mercury sits to our own Sun by a wide margin. At that range, whatever the star produces, in light, in radiation, in charged particles, arrives at the planet essentially undiluted by distance. There's no room for the intensity to fade before it gets there. So we're left with a picture of a planet that, even setting aside everything discussed about its violent youth, orbits close enough to a chronically unstable star that it experiences this kind of event on a near constant basis, not as an occasional hazard, but as an ongoing condition of its existence. The question that raises, and the one we'll spend the next stretch of this story answering carefully, is what that kind of exposure actually does to a planet's atmosphere over time. Not in theory. In the specific measured events astronomers have actually caught happening. In April of 2019, a network of observatories caught something unusual happening at Proxima Centauri, a flare so powerful that had the star been close enough and the timing right, it would have been visible to the unaided human eye. Astronomers led by Meredith McGregor and colleagues, and separately documented by researchers including Howard and collaborators, measured the event's total energy output at somewhere in the range of 10 to the power of 33 ergs, a figure that on its own means very little to most people, so it's worth translating. A useful reference point is something called the Carrington event, a solar flare that struck Earth in 1859, the most powerful eruption our own sun has produced in recorded history. It was intense enough to set telegraph equipment on fire and paint auroras as far south as the Caribbean. The 2019 flare, observed at Proxima Centauri, released roughly 10 times more energy than that. 10 times the strongest flare our own well-behaved sun has thrown at us in the past 2 centuries. And for Proxima, this wasn't a once-in-2 centuries anomaly. Based on tracking data going back years, researchers estimate flares of this rough magnitude occur something like 8 times a year at this star. Not once a generation, multiple times annually, indefinitely, for as long as the star has existed in its current active state, which, given how slowly red dwarfs age, could mean for most of its multi-billion-year life so far. I keep coming back to this specific number whenever I revisit the research, because it never quite settles into feeling ordinary. 10 Carrington events, roughly several times a year, aimed at a planet sitting close enough to receive it in full. It's not a figure that gets less strange the more familiar you become with it. What actually happens to a planet on the receiving end of an event like this is worth walking through carefully, because the mechanism matters as much as the raw energy. When a flare's ultraviolet and X-ray radiation strikes a planet's upper atmosphere, it ionizes the gas there, essentially stripping electrons off atoms and molecules. Those newly freed electrons, being extremely light, gain enough energy from the process to escape the planet's gravity outright, flying off into space. But electrons carry a negative charge, and as they leave, they create a charge imbalance behind them. Opposite charges attract, so as the negatively charged electrons pull away, they drag the heavier, positively charged ions along with them out of the atmosphere entirely. It's not a single mechanism stripping the sky away. It's a kind of electrical cascade, the small particles pulling the larger ones out behind them. This is a well-documented process, studied directly at Earth during periods of intense solar activity, and modeled specifically for Proxima b by researchers, including a team at NASA who ran simulations placing a hypothetical Earth twin, complete with an Earth-strength magnetic field, at Proxima b's exact orbital position and radiation exposure. The result of that modeling wasn't reassuring. Even with Earth's own magnetic shielding, the simulated planet lost atmosphere at a rate far beyond anything Earth itself experiences, because the shielding that works well against our sun's comparatively mild output isn't matched to what a star like Proxima routinely produces. The total dose adds up over time in a way that's easy to underestimate if you only think about individual flares in isolation. Researchers working from decades of combined observational data put Proxima B's lifetime exposure to high-energy ultraviolet and X-ray radiation somewhere between 8 and 25 times greater than what Earth has received from the Sun across its own history. Not per flare, across the planet's entire existence, compounded. For context, that's not the difference between a mild climate and a harsh one. That's the difference between the radiation environment that allowed Earth's atmosphere and oceans to persist for 4 billion years, and one capable of steadily eroding both, one flare at a time, for as long as the star keeps producing them, which, given what we know about how red dwarfs behave over their lifespans, is likely to be a very long time yet. So even setting aside everything discussed earlier about the planet's early history, even in the most generous version of that earlier story, where some water survived the runaway greenhouse phase intact, this is what it would still be facing today. Not a single bad event millions of years in the past, but an ongoing, unrelenting condition written into the fundamental nature of the star itself. It helps, at this point, to step back from individual flares and individual numbers and ask a simpler question. Compared to what Earth actually experiences, day to day, how much worse is this really? The comparison researchers most often reach for involves stellar wind, the constant outward stream of charged particles every star emits, distinct from the sudden bursts of a flare. Our own sun's stellar wind is part of ordinary space weather, deflected almost entirely by Earth's magnetic field, occasionally strong enough to produce visible auroras, but never strong enough to threaten the atmosphere itself. Estimates for what Proxima b experiences from its star's combined wind and flare activity put the intensity at more than 2,000 times what Earth receives from the Sun. 2,000 times isn't a figure that translates easily into felt experience, so it's worth trying a different kind of comparison. Imagine the total amount of solar radiation Earth absorbs in an average year, everything from the gentle daily sunlight to the occasional solar storm. Now imagine compressing 2,000 years of that same total exposure into a single year. That's roughly the order of magnitude we're talking about, not spread out gently across time, but delivered continuously, year after year, to a planet that, unlike Earth, has no confirmed magnetic field of its own to help absorb it. This is where the story requires a genuine pause on what we don't know, because the honest scientific position is more careful than the planet has no protection at all. We simply don't know whether Proxima b has a magnetic field. Earth's magnetic field is generated by the churning of molten iron in our planet's core, a process tied to the planet's internal heat, its rotation, and its composition, none of which we can currently measure for a world 4 light-years away. It's entirely possible Proxima b has some magnetic field. It's also entirely possible it has none, or one too weak to matter. What research teams have done instead is model both cases, and the results of that modeling are worth sitting with. A study led by NASA researcher Chuanfei Dong and colleague Cristina Garcia Sage placed a hypothetical version of Earth, complete with Earth's actual magnetic field strength, at Proxima b's orbital distance and radiation environment, then ran the physics forward to see what would happen. Even with full Earth-strength shielding, the simulated planet lost its atmosphere at a rate far exceeding anything Earth itself experiences, fast enough that over a period of time far shorter than the planet's actual age, an Earth-like atmosphere would be substantially depleted. And this was described explicitly as a conservative estimate. The model didn't include the most extreme flare events, the ones like the 2019 super flare. It used average conditions. The results were still not encouraging. This is where I find myself every time I revisit this particular calculation, doing something close to what the paper's own co-author did. Jeremy Drake, an astrophysicist involved in related modeling work, was blunt about it in describing the implications. Atmospheric loss rates at this level make habitability, in his words, implausible. Not impossible in some absolute philosophical sense. Implausible given everything the physics tells us. I don't think implausible is a word scientists use lightly, and it's worth noticing what it's doing here. It isn't a dramatic word, it's a careful one. It leaves the door open by exactly as much as honest uncertainty requires, and not 1 inch further. What all of this means, taken together with the runaway greenhouse phase from Proxima B's youth, is that this is a planet facing not one obstacle to habitability, but at least 2 entirely independent obstacles, each one on its own capable of stripping the world of what it would need to support life as we understand it. The early water loss happened once, catastrophically, in the planet's first 200 million years. The ongoing radiation exposure has been happening continuously since, and shows no sign of stopping because it's simply what this particular kind of star does for its entire life. If Proxima b started with enough water to survive its youth, the ongoing radiation environment represents a second, separate threat to whatever it managed to keep. If it lost everything in its youth, the ongoing radiation environment is simply confirmation that nothing would have had the chance to return since. Either way, the path toward a habitable outcome here has narrowed considerably, not because of a single dramatic event, but because of 2 separate, independently verified physical processes, both pointing in the same direction. There's one more piece of this particular puzzle left to examine, and it has nothing to do with radiation at all. It has to do with the planet's orbit itself, and what happens to a world that circles its star close enough to complete a full year in just 11 days. There's a natural question that follows from everything so far, and it deserves its own real attention rather than a passing mention. What if Proxima b does have a magnetic field? Would that change the story? Earth's magnetic field isn't a minor detail in our planet's survival. It's generated deep in the core, where molten iron churns and rotates, producing a field that extends far out into space, deflecting the bulk of the sun's charged particles before they ever reach the upper atmosphere. Without it, Earth's own atmosphere would be far more vulnerable than it is. Mars is the case study most often cited for what happens without one. A planet that likely had a magnetic field early in its history, lost it as its core cooled, and has spent billions of years since watching its atmosphere thin under the sun's stellar wind, until what remains today is a fraction of 1% of Earth's atmospheric pressure. So, a magnetic field matters. The question is whether Proxima b has one, and here the honest answer is that nobody knows, because there's currently no way to measure it directly. A planet's magnetic field depends on factors like its rotation rate, the composition and temperature of its interior, and whether it has a molten, convecting core at all, none of which we can observe from 4 light-years away with current instruments. What researchers have been able to do is model different scenarios and see how much a field, if one exists, would actually help. And the results are more sobering than you might expect. Even a magnetic field roughly as strong as Earth's, modeled against Proxima's radiation environment rather than the Sun's, doesn't hold up the way it does here. The field can deflect the lower energy particles reasonably well, much as it does at Earth. But Proxima's flares regularly produce far more energetic events than anything the Sun typically manages, and the most energetic particles simply aren't stopped by a magnetic field of ordinary strength. They punch through. There's also a mechanical problem specific to how close Proxima b orbits its star. A planet's magnetic field forms a protective bubble called a magnetosphere, and the size of that bubble depends partly on how hard the star's stellar wind is pushing against it from outside. Push hard enough, and the magnetosphere compresses, shrinking down toward the planet's surface rather than extending safely out ahead of it. At Proxima b's distance, with stellar wind pressure potentially thousands of times what Earth experiences, some models suggest the magnetosphere could be compressed so severely that it offers only partial protection, even in the best case, with a strong field and everything working as well as it possibly could. This is genuinely uncertain territory, and it's worth being precise about what kind of uncertainty it is. It's not that scientists disagree about the physics. The physics of magnetospheres and stellar wind pressure is well understood, tested directly at Earth and at other planets in our own solar system. The uncertainty is entirely about the specific, unmeasurable properties of one particular planet, whether it has a molten core, how fast it rotates, whether any field it generates is strong enough to matter given what it's up against. Every one of those questions currently has to be answered with, "We don't know," not because the science is unsettled, but because the planet is too far away and too small for any instrument we currently have to check. If you've spent any time with this channel before, you may remember a night we spent on a different piece of this same story. The sheer scale of the journey to get there, what it would actually take for a spacecraft or a person to close that 4 light-year gap. Tonight's story lives on the other side of that same distance. That distance is exactly why questions like this one, whether a specific unreachable planet has a magnetic field, tend to stay open for a very long time. There's no probe currently en route that could answer it, and even the fastest theoretical proposals would take decades just to arrive, decades more before any data made its way back. So we're left again with careful uncertainty rather than a clean answer. A magnetic field, if Proxima b has one, would help. It wouldn't necessarily be enough, given how much more hostile this star's radiation environment is compared to our own sun's, and given how close the planet's orbit sits to the source of that hostility. It's one more variable stacked on top of the others already discussed, each one narrowing the range of scenarios where this planet ends up somewhere survivable without eliminating that range entirely. There's one part of Proxima b's situation we haven't touched yet, and it has nothing to do with the radiation or magnetic fields. It has to do with what an orbit this close actually does to a planet's day, and its night, and everywhere in between. There's one more consequence of orbiting this close to a star, And it has nothing to do with radiation at all. It has to do with something far more basic, the shape of a day. Proxima b completes a full orbit around its star in just 11.2 days, at a distance of roughly 4.6 million miles, about 5% of the distance between Earth and the Sun. That proximity, combined with the star's gravity acting on the planet over a long span of time, makes it very likely that Proxima b has become what astronomers call tidally locked. Tidal locking is a familiar phenomenon, even if the name isn't. It's the same process that keeps the moon showing Earth only one face, forever. The same craters and seas pointed toward us, regardless of where the moon sits in its orbit. Over enough time, a star's gravity pulls slightly harder on the near side of an orbiting planet than the far side, creating a gentle but persistent twisting force. That force gradually slows the planet's rotation until it matches its orbital period exactly, at which point the twisting stops, because the planet is no longer rotating relative to the star at all. One side faces the star permanently, the other faces away permanently. For a planet orbiting as close to its star as Proxima b does, tidal locking isn't a possibility among several. Given enough time, and the system is old enough to have provided plenty, it's close to the expected outcome. So the most likely scenario is a planet with one hemisphere locked in perpetual daylight and one locked in perpetual dark, with no dawn, no dusk, no ordinary day ever arriving on either side. Picture what that actually means, stripped of the astronomy. On the day side, the sun the planet orbits never moves, sitting fixed in the same spot in the sky, permanently, for as long as the planet has existed in that configuration. There's no sunset to look forward to, because sunset isn't a concept that applies. On the night side, the reverse. A sky that has never once seen daylight, not for an hour, not for a moment, in the entire history of the planet. The consequences for climate follow directly from that geography. The day side, absorbing constant direct radiation with nothing to interrupt it, would likely run extremely hot, potentially hot enough to keep any atmosphere in a permanent state of turbulent, storm-driven circulation, trying and failing to move heat away fast enough. The night side, receiving no starlight at all, would run correspondingly cold, potentially cold enough for any atmosphere present to freeze out entirely, falling as frost or snow onto a surface that never sees the light that might otherwise warm it back into gas. There's a real physical risk buried in that last detail, one that researchers who model these planets take seriously. If a tidally locked planet's atmosphere is thin enough, or its night side cold enough, the atmosphere itself can effectively collapse, condensing out of the sky and settling permanently onto the frozen night side as ice, leaving the day side with progressively less atmosphere to work with over time. In the most extreme version of this scenario, a planet can lose the ability to move heat around entirely, trapped in a feedback loop where the very thing that might have made it habitable, an atmosphere thick enough to redistribute warmth, becomes the thing its own geography slowly strips away and buries. This is, again, not a certainty. It depends heavily on how thick the atmosphere is to begin with, which circles back to every uncertainty already discussed. How much water and gas the planet retained through its violent use. How much has been stripped since by ongoing radiation? Whether a magnetic field offers any meaningful protection. A sufficiently thick atmosphere can, in principle, move enough heat between the two hemispheres to prevent the worst of this collapse, keeping both sides within a survivable range, even without a normal day-night cycle to do the work. A thin one likely can't. What's true regardless of atmospheric thickness is the underlying geography itself. There is no dawn on this planet, and there never will be. Not as an occasional event, not as something that happens once and then doesn't happen again for a while. The star simply doesn't move across this planet's sky, ever, in either direction. Whatever kind of world exists there, whatever survives on it or doesn't, exists inside a permanent, unchanging relationship with its star that has no real analog anywhere in our own solar system, not even close. It's a strange kind of stability, not the reassuring kind where conditions stay pleasant because nothing threatens to disturb them, the kind where nothing changes because the geometry itself has frozen in place permanently, and everything that might have varied, temperature, light, the ordinary rhythm of a day, has instead locked into two fixed and radically different extremes with only a thin boundary between them. That boundary, the line separating permanent day from permanent night, turns out to be the one place in this entire picture where the story gets slightly less bleak. It's worth spending real time there before we leave Proxima Centauri behind for the other two stars in this system. If there's a version of Proxima b that stands any real chance, it isn't the blazing day side or the frozen night side. It's the thin strip of territory between them, the terminator, the line where day meets night and neither fully wins. On a tidally locked planet, the terminator isn't a boundary that sweeps across the surface the way sunrise and sunset do here. It's fixed in place, permanently, wrapping around the planet like a ring, running from pole to pole along the line where the star's light arrives at a grazing angle rather than shining straight down. Researchers modeling Proxima b's potential climate, including detailed work using global circulation models originally built to study Earth's own atmosphere, have found that this ring-shaped zone could, under the right conditions, sit at temperatures moderate enough for liquid water, even while the two hemispheres on either side of it swing to punishing extremes. The logic behind this is fairly intuitive once you picture it. Directly under the star, on the day side, sunlight strikes the surface at close to a right angle, delivering maximum energy per square mile. Near the terminator, that same sunlight arrives at a shallow, glancing angle, spreading the same amount of energy across a much larger area. The same basic geometry that makes early morning and late evening light gentler here on Earth than the light of high noon. A planet with enough atmosphere to move some heat around, but not so tidally locked and airless that the whole system collapses, could plausibly maintain a narrow habitable ring exactly where day gives way to night. This isn't a settled conclusion so much as a genuinely live area of ongoing modeling, and the honest caveat is the same one that shadowed most of this story. It depends entirely on how much atmosphere the planet has left, a number nobody currently has direct access to. There's a second, more specific concern that applies even within this narrow ring, and it circles back to something covered earlier: the flares. Even in the terminator zone, where temperatures might sit in a survivable range, the planet is still orbiting a star that produces roughly 10 times the energy of Earth's most severe recorded solar event, several times a year, indefinitely. A team of researchers looking specifically at this question calculated what the strongest flares Proxima b has been observed to produce would do to surface conditions, even in the most favorable location on the planet, and even accounting for the strongest flare events documented at Proxima Centauri. Their finding was cautiously specific. Ultraviolet damage from even the largest observed flares could plausibly be avoided by anything living at a water depth of roughly 9 meters or more, since water itself blocks ultraviolet light far more effectively than a thin atmosphere does on its own. 9 meters, not a continent-scale refuge, a specific, calculable depth, deep enough that flare radiation simply can't reach whatever might be living below it, while still shallow enough that sunlight, filtered and weakened but present, could still support something like photosynthesis. It's a strange kind of habitability to imagine, if it exists at all. Not sunlit fields or open coastlines, the way habitability tends to get pictured by default, but a narrow underwater refuge along a ring that never moves, on a planet where the sky itself never changes, shielded from a star that spends its entire existence trying to strip away whatever managed to survive this far. What this section is not meant to do is quietly reverse everything established before it. The Terminator scenario requires nearly everything discussed earlier to have gone the more forgiving way. Enough water surviving the runaway greenhouse phase of the planet's youth. Enough atmosphere surviving the ongoing radiation exposure since. Enough thickness in that atmosphere to prevent the night side from freezing the whole system solid. Each of those is, individually, the less likely branch in the physics as currently understood. Stacking 3 or 4 less likely branches on top of each other doesn't make the combined outcome more probable. It makes it a genuine long shot, worth naming honestly as a long shot, rather than dressed up as quiet hope. But it isn't nothing either. It's the one place in this entire analysis where the physics doesn't close the door completely, where a planet built almost entirely out of hostile extremes might still carve out a narrow specific exception for itself, provided enough of the uncertain variables happen to break the same way. We've spent a long time now with just one star and one planet. It's worth remembering there are 2 more stars in the system, and they face an entirely different set of obstacles, ones that have nothing to do with flares or runaway greenhouses at all. Everything discussed so far has been specific to Proxima Centauri, a small, dim, chronically unstable red dwarf, and to the one confirmed planet orbiting close enough to feel every consequence of that instability. It would be reasonable, at this point, to expect the other 2 stars in the system to fare better. They're larger, calmer, and in most respects, genuinely similar to our own Sun. Alpha Centauri A and Alpha Centauri B orbit each other closely, completing one loop around their shared center of mass roughly every 80 years. Alpha Centauri A, the larger of the 2, is a G-type star like the Sun, about 10% more massive and roughly 1.5 times as luminous. Its habitable zone, the region where a planet could plausibly maintain liquid water, sits somewhere between about 1.2 and 2.1 astronomical units from the star, a bit farther out than Earth's orbit, owing to A's slightly higher brightness. Alpha Centauri B is smaller, a K-type star, about 90% the Sun's mass and roughly half its brightness. Its habitable zone sits closer in, somewhere between about 0.7 and 1.2 astronomical units, close to where Earth orbits our own Sun. Neither star behaves anything like Proxima. Neither is fully convective. Neither produces the kind of relentless, 10 times Carrington flares that define Proxima's ongoing relationship with its planet. If either star hosted a rocky planet in its habitable zone, that planet wouldn't be facing anything close to the radiation environment Proxima b endures. In terms of stellar temperament alone, both A and B look like genuinely promising places to search, which is exactly why the search has been going on seriously and persistently for decades. So, it's worth being precise about what that search has actually found so far, because the honest answer is nothing confirmed. Not yet. There have been candidates, some of them promising enough to generate real excitement at the time, and every one of them, so far, has either turned out to be a false signal or remains unconfirmed years after it was first proposed. In 2012, a team reported detecting a signal in Alpha Centauri b's data consistent with a planet, quickly named Alpha Centauri bb. It made headlines as the closest known exoplanet to Earth at the time. By 2015, a more careful reanalysis of the same data concluded the signal was very likely an artifact of the observing process itself, not a real planet. Alpha Centauri bb was quietly retracted from the roster of confirmed worlds. In 2013, a possible planetary transit was reported in the same system, a brief dimming of starlight consistent with the planet passing in front of its star. Follow-up analysis suggested that even if real, the object would have been orbiting too close to its star to be a plausible candidate for habitability, and the signal itself was never conclusively confirmed as planetary in origin. In 2021, using direct thermal imaging rather than the indirect wobble or transit methods used in the earlier attempts, a team detected something they designated Candidate 1, a possible planet or planet-forming disk feature near Alpha Centauri A, sitting intriguingly close to that star's habitable zone. It remains to this day unconfirmed, not disproven, not verified, sitting exactly where the earlier signals also sat, in the space between a real discovery and a false one, waiting for better data to settle the question either way. 3 separate signals, 3 separate decade-spanning efforts, and not one of them has yet crossed the line into confirmed discovery. That's not a small or ordinary run of bad luck. In a system this close, this bright, this thoroughly studied by multiple independent teams using multiple different detection techniques, the repeated failure to confirm even a single planet around either A or B starts to look less like an observational gap and more like a real feature of the system itself. The obvious next question is why? Why would 2 stars this calm, this sun-like, this seemingly well-suited to hosting planets, have such a difficult time producing confirmed ones, when far more distant and far harder to observe systems have yielded thousands of confirmed exoplanets in the same span of time? The answer isn't about the stars themselves. It's about what it means to try to form a planet in a system where 2 stars, not one, are pulling on everything in it. Every planet that has ever formed anywhere started the same way, as a disk of gas and dust orbiting a young star, gradually clumping together through countless small collisions, pebbles becoming boulders, boulders becoming planetesimals, planetesimals slowly assembling into the planets we eventually see. It's a slow, patient process, and it depends on those small collisions being gentle enough to stick rather than violent enough to shatter. Around a single star, orbiting on their own, planetesimals mostly move in calm, predictable paths, colliding at low relative speeds, building up mass gradually over millions of years. around a binary star system, that calm picture changes. Alpha Centauri A and B don't orbit each other in a neat circle. Their orbit is eccentric, meaning the distance between them varies significantly over the course of each roughly 80-year cycle. At their closest approach, called periastron, the two stars come within about 11 astronomical units of each other, closer than the distance between our own Sun and Saturn. At their farthest, apoastron, they separate to about 35 astronomical units, farther than Pluto's average distance from the Sun. That variation matters enormously for anything trying to form a planet around either star. Each time the companion star swings through periastron, its gravity reaches into the other star's planet-forming disk and stirs it, speeding up the orbital velocities of the material there, particularly in the outer regions of whichever star's disk is being disturbed. Higher velocities mean more violent collisions, and violent collisions, instead of gently sticking planetesimals together, tend to shatter them apart. A study published in 2009 modeled exactly this process for planetesimals attempting to grow within Alpha Centauri A's habitable zone, and found that the growth process becomes only marginally possible, even fairly close to the star, around half an astronomical unit out. Beyond that distance, closer to where the actual habitable zone sits, the companion star's periodic gravitational stirring made ordinary planetesimal accretion, the basic building block of planet formation, essentially impossible. This is worth sitting with because it's a genuinely different kind of obstacle than anything discussed with Proxima b. Proxima's planet appears to have formed, appears to have existed, and then faced threats from radiation and water loss afterward. What this research suggests for Alpha Centauri A and B is a problem earlier in the process. It's not that a planet formed in the habitable zone and then something damaged it. It's that forming a rocky planet there at all, out of the raw material available, may simply be much harder than it would be around an isolated star with no companion regularly disturbing the neighborhood. It's not impossible. More than 12% of all confirmed exoplanets discovered anywhere in the galaxy orbit stars that are part of binary or multiple systems, so binarity on its own clearly doesn't rule planet formation out entirely. Some theoretical studies, running simulations specifically for a system shaped like Alpha Centauri, have found configurations where multiple planets do successfully form, including at least one in the rough size range of Earth. The physics doesn't forbid it. It just makes the ordinary process considerably less forgiving, narrowing the range of conditions, initial disk masses, particle sizes, formation timelines, under which a habitable planet could plausibly assemble itself before the companion star's gravity had a chance to interfere. What that leaves us with is a system where the difficulty isn't concentrated in one dramatic obstacle, the way Proxima's violent flares are. It's distributed across the entire formation process itself, a persistent headwind rather than a single storm, one that would have been present for every planetesimal, every protoplanet, every stage of assembly, for as long as the disk of raw material around either star existed. This helps explain something that might otherwise seem strange: why 3 separate detection efforts, spanning nearly a decade and using increasingly sophisticated instruments, have failed to confirm even one planet around either Alpha Centauri A or B in a system close enough and bright enough that we can study it in far more detail than almost anywhere else in the galaxy. It's not primarily a limitation of our telescopes. It may be a reflection of what actually happened or didn't happen in that system billions of years ago, when the raw material for planets was still there, and the two stars now taking up most of the sky between them were young enough to still be pulling that material apart before it had the chance to become anything at all. None of this means the search has stopped. If anything, the difficulty of the problem has made the ongoing effort to answer it more interesting, not less. And there are people right now using instruments built specifically for this system, still looking. Given how difficult this system has proven to search, it's worth understanding what astronomers are actually doing about it right now, because the effort hasn't stopped. If anything, the repeated near misses have sharpened the tools being built to finally settle the question. The most direct current effort is a mission called Ptolemy, an acronym for Telescope for Orbit Locus Interferometric Monitoring of our astronomical neighborhood, though the name is also a deliberate nod to Ptolemy, an older name for Alpha Centauri itself. The mission is led by Peter Toothill, an astrophysicist at the University of Sydney, working alongside the breakthrough initiatives, Sabre Astronautics, and NASA's Jet Propulsion Laboratory. Toothill has described the appeal of the target plainly. In the vast scale of the galaxy, Alpha Centauri sits, in his words, tantalizingly close to home. What makes Ptolemy interesting isn't just its target, it's the design of the telescope itself. Rather than focusing starlight into the tight, sharp point that conventional telescopes aim for, Ptolemy uses what's called a diffractive pupil, a specially patterned mirror that deliberately spreads incoming starlight into a complex, flower-shaped diffraction pattern. That might sound like it would make measurements harder, but it does the opposite. By spreading the light out into a detailed, structured pattern, rather than a single bright point, the instrument becomes far more sensitive to the tiny, telltale shifts in that pattern, caused by an unseen planet's gravity tugging the star very slightly back and forth. It's a technique built specifically to catch a wobble too small for most instruments to notice, aimed at exactly the two stars that have resisted confirmation for over a decade. The mission is currently in its second development phase, with the telescope and its integration into a satellite platform actively underway. It hasn't launched yet. When it does, its first and primary targets will be Alpha Centauri A and B, the same two stars responsible for 3 separate rounds of tantalizing, unconfirmed signals. Ptolemy isn't the only tool being brought to bear on this problem. The James Webb Space Telescope, launched in 2021 for an enormous range of astronomical purposes, has also turned its attention here. A research team using JWST's mid-infrared instrument, working in coronagraph mode, a technique that blocks out a star's overwhelming glare to reveal much fainter objects nearby, conducted a deep search specifically targeting Alpha Centauri A's habitable zone, published in 2025. Working in mid-infrared wavelengths offers a specific advantage here. Alpha Centauri A's glare, so overwhelming in visible light that it drowns out anything faint nearby, is considerably less blinding at these longer wavelengths, making it theoretically possible to spot something like the unconfirmed candidate, one signal from 2021, if it's real, or to finally rule it out if it isn't. What's notable about both of these efforts, Ptolemy and the JWST search, is that neither one is chasing a hunch. Both are responses to a specific, unresolved scientific question that has persisted for over a decade. Does this system, so close, so bright, so thoroughly studied, actually contain a rocky planet in either star's habitable zone? Or does the difficulty of forming one there, the gravitational disruption discussed in the last section, mean the answer has been no all along? It's a genuinely open question, in the fullest sense of that phrase. Not open because nobody has looked hard enough. Open because the tools capable of looking hard enough are only now being built and deployed, aimed at a target that has quietly resisted every previous attempt. There's something worth noticing in the fact that this effort continues at all, given everything covered so far tonight. A star's early violence can wound a planet before it has a chance to exist. A companion star's gravity can prevent a planet from forming in the first place. And still, astronomers keep building better instruments, keep aiming them at the same 3 stars, keep trying to answer a question that the evidence so far has mostly answered with silence. That's not naivety. It's closer to the ordinary, unglamorous persistence that most real scientific progress actually looks like. Not a single triumphant discovery, but years of instruments getting slightly better, models getting slightly more precise, and researchers returning again and again to the same unresolved question. Because the question hasn't gone away, just because the early answers were discouraging. It's worth pulling everything together now, not to repeat what's already been covered, but to see the shape it makes when placed side by side, because 3 very different mechanisms have led to what looks, from a distance, like the same basic outcome. Proxima Centauri b sits in a habitable zone that is real, calculated correctly, no different in principle from the zone that keeps Earth's water liquid. What compromises it isn't the zone itself, it's the star. A young, violently overluminous phase lasting up to 200 million years that likely stripped away most or all of the planet's original water, followed by an ongoing, permanent condition of flares and radiation exposure, roughly 2,000 times what Earth experiences, a condition that shows no sign of easing, because it's simply what a fully convective red dwarf does for the majority of its extremely long life. Layered on top of both of those, an orbit close enough to guarantee tidal locking, freezing the planet into a permanent daylight hemisphere and a permanent night hemisphere, with only a narrow, uncertain ring at the boundary, offering any real chance at moderation. That's one confirmed planet, facing at least 3 independent compounding threats, each one capable on its own of ending the story. There's a second confirmed planet in this system worth naming properly, one that hasn't come up yet tonight. Proxima Centauri c, first reported in 2019 by a team led by Mario Damaso, is a much larger world, roughly 7 times the mass of Earth, orbiting its star far more distantly than Proxima b does, taking about 5.2 years to complete one loop. At that distance, Proxima c sits well outside the habitable zone, cold enough that liquid water on any solid surface isn't a serious consideration, regardless of what else might be true about it. It isn't a candidate for habitability in the way Proxima b is. It's simply further evidence that this star hosts a genuine planetary system, not just one lonely world, and that whatever violence Proxima Centauri directs at its inner planet, its outer planet has been spared the worst of it, purely by virtue of distance. Then there's Alpha Centauri A and B, the 2 sun-like stars that, on the basis of temperament alone, should have been the easier case. Calm, stable, none of Proxima's chronic flaring. And yet, after 3 separate detection campaigns spanning more than a decade, not one confirmed planet has emerged from either star's system. The obstacle here isn't radiation. It's earlier than that, embedded in the physics of trying to build a planet at all, in a system where a second star's gravity periodically reaches in and stirs the material that planet would need to be made from. Line these up, and a pattern starts to emerge, though it's worth being careful about what kind of pattern it actually is. It isn't that space is uniformly hostile, or that habitable zones are a meaningless concept, or that every star system will inevitably turn out this way. Plenty of exoplanets discovered elsewhere in the galaxy remain genuinely open, uncertain candidates for habitability, with no equivalent smoking gun ruling them out the way the evidence here increasingly does. What's specific to Alpha Centauri is that this particular system, for reasons entirely its own, seems to have accumulated an unusually thorough set of independent obstacles. A red dwarf with an unusually violent developmental history and an unusually active adult life. A pair of sun-like stars locked in an orbital dance eccentric enough to actively interfere with the basic mechanics of planet formation. 3 stars. 3 different reasons, each verified through separate lines of research, each pointing in roughly the same direction. Not a single dramatic verdict delivered all at once, but 3 quiet ones, arrived at independently by different research teams using different instruments over the better part of a decade that happened to agree with each other by the time you set them side by side. This is where the phrase in tonight's title earns its weight, and where it's worth being precise about what it does and doesn't claim. Nothing covered tonight is a direct observation of a dead world. No probe has visited Proxima b. No instrument has confirmed or denied a magnetic field, an atmosphere, an ocean. What exists instead is a convergence. Several independent physical processes, each modeled and verified on its own terms, each one individually capable of ending a planet's chance at habitability, and all 3 somehow present in the same small, close, thoroughly studied system that first gave us reason to hope back in 2016. Convergent evidence isn't the same as direct proof. It's what you have instead of direct proof. When direct proof is 4 light years away and likely to stay that way for a very long time, it's also, in its own way, a stronger kind of confidence than any single dramatic finding could offer, because it doesn't rest on one measurement being right. It rests on several different measurements, taken independently, all landing in the same place. There's a specific discomfort in a phrase like already dead, and it's worth naming directly rather than letting it sit unexamined for the rest of this story. Dead implies something was once alive. Nothing covered tonight establishes that any of these worlds ever hosted life, not even in the most speculative sense. What the evidence actually supports is narrower and, in its own way, stranger, that the conditions necessary for life, as we understand it, appear, independently and repeatedly, to have failed to persist, or perhaps failed to ever fully arrive. On every world in this system, we've been able to study closely enough to say anything definite about. That's not quite the same claim as, these worlds are dead. It's closer to, these worlds appear to have been denied the chance, at multiple separate points, by multiple separate mechanisms, well before the question of life could have become relevant at all. I've sat with this distinction longer than I expected to, working through this particular story, because it would have been easy to let the title's promise flatten into something simpler than what the research actually supports. It would have been easy to say, simply, these worlds are dead, full stop, and move on to the next dramatic claim. What the evidence actually offers is quieter and more honest than that, and I think the quieter version is the one worth keeping. Proxima b likely lost most of its water before its star had even matured. It has likely lost more since, continuously, to a level of radiation exposure that one of the researchers involved described, carefully, as making habitability implausible. Its neighbors, orbiting the two calmer stars nearby, may never have successfully formed as rocky planets in their habitable zones at all, not because something happened to them afterward, but because the raw material may never have been permitted to properly assemble in the first place. Implausible isn't impossible. Never fully formed isn't the same claim as destroyed. The honest verdict this evidence supports cites somewhere in that space a convergence of independent, well-documented physical processes, each one narrowing the range of survivable outcomes, without a single one of them delivering absolute, unambiguous proof. What I keep returning to, turning this over, is that this verdict doesn't require any sense of tragedy to be true. There's a temptation, telling a story like this one, to reach for loss as the governing emotion. The tragedy of a world that could have been habitable and wasn't, robbed of its chance by forces beyond anyone's or anything's control. That framing isn't wrong exactly, but it imports something that isn't really there. Tragedy requires a life that was interrupted, a story that was cut short. What actually happened at Alpha Centauri, as best the evidence can currently tell it, is closer to a set of conditions that simply never lined up, the way most conditions across the overwhelming majority of the universe simply don't. That's not a small distinction. It changes what kind of story this actually is. Not a graveyard exactly. Something closer to an accounting. A careful, honest tally of the specific reasons. 3 worlds sitting in what looked from a distance like exactly the right place turned out not to be. If there's a verdict worth holding on to by the end of tonight, it's this one, stated as plainly as the evidence allows. The habitable zone got these 3 worlds their invitation. It didn't get any of them through the door. What stood in the way wasn't one dramatic obstacle, but several ordinary ones. A violent stellar youth here, a companion star's disruptive gravity there, each one unremarkable on its own, each one simply doing what physics does, and each one, taken together, sufficient to explain why the nearest star system to our own has so far offered us nothing we can point to and call, with real confidence, a living world. That's not a comfortable ending exactly. It's not meant to be a comfortable one, but it isn't a grim one either. Not really once you sit with it long enough. It's simply what an honest accounting looks like, delivered without the exaggeration that would make it easier to package, and without the false hope that would make it easier to hear. There's still one more question worth asking before we're done tonight, and it's a fair one. If the evidence points this consistently in one direction, why does anyone keep looking at all? Why build a mission like Taliman? Why point the James Webb Space Telescope at a system that has offered so little in return for so much attention? The answer turns out to have very little to do with optimism, and quite a lot to do with what it actually means to find nothing, carefully and on purpose. There's a version of this question that assumes finding nothing is a kind of failure, that all this careful modeling and all these instruments, Tolman, JWST, decades of radial velocity data, only really pay off if they eventually locate a living world. That assumption is worth setting aside, because it isn't how the actual value of this kind of search works. If the evidence from Alpha Centauri continues to point the way it currently does, toward 3 worlds that never quite crossed into habitability, that finding still tells us something real. Not about this one system in isolation, but about the broader question of how common life-bearing planets are likely to be, anywhere. Consider what the alternative would look like. If the nearest star system to our own, studied more thoroughly than almost any other system in the galaxy, with 3 genuinely different stellar environments to test against, turned out to easily produce a habitable, life-supporting world that would suggest habitability is common, that the specific sequence of conditions Earth happened to receive isn't especially rare. What the evidence actually suggests instead, cautiously and with real uncertainty still attached, is closer to the opposite, that even a system with 3 separate chances, 3 different stars, 3 different sets of starting conditions, appears to have come up empty on all 3 counts, for 3 entirely different physical reasons. That's genuinely informative, even though it isn't the finding anyone was originally hoping for back in 2016. It suggests that whatever allowed Earth to keep its water, keep its atmosphere, keep a magnetic field strong enough to matter, and an orbit stable enough to avoid tidal locking, wasn't the easy default outcome. It was a specific alignment of conditions that, at least in this one nearby case, simply didn't repeat. There's a way of thinking about this that reframes the entire premise of searching for life among the stars, one that doesn't require finding anything to feel meaningful. If most of the universe genuinely is empty of life, then every habitable world life eventually reaches isn't taken from anyone. It's not displacement. It's not arrival into a world that was already someone else's. It's closer to filling a niche that had simply never been filled before, on a scale that, if the pattern at Alpha Centauri holds more broadly, may turn out to be the ordinary condition of most of the galaxy, rather than the exception. That reframing doesn't erase the honest uncertainty running through everything discussed tonight. We don't know for certain that Proxima b has no water left. We don't know for certain that Alpha Centauri A and B never managed to form a rocky planet in their habitable zones. Only that the search so far has failed 3 separate times. Tolman hasn't launched yet. The JWST search continues. Any of these conclusions could still shift, meaningfully with better data. But it does explain why the search continues regardless of what the current evidence suggests, and why that continuation isn't naive. Every result, whether it eventually confirms a planet or rules one out for good, adds to a much larger, slower project. Understanding how rare or how common the specific set of conditions that produced Earth actually is, across the only sample size we currently have access to, one nearby star system at a time. Alpha Centauri, for all the disappointment layered into tonight's story, remains one of the most valuable places in the sky to keep asking that question, precisely because it's close enough to actually get real answers, rather than educated guesses. Every other star system we study for habitability sits so far away that our conclusions are necessarily statistical, built from populations of exoplanets rather than detailed knowledge of any single one. Alpha Centauri is different. It's close enough that the answers, whatever they turn out to be, can be specific rather than general, earned rather than inferred. That's worth something on its own, independent of whether the final answer turns out to be the one anyone was originally hoping for. 3 stars, 3 different stories, and 1 nearby. Unusually thorough answer to a question that most of the rest of the galaxy can only offer us in vague, statistical terms. We're near the end of what tonight has to cover. What's left is smaller than everything that came before it. A chance to step back from the physics entirely and sit for a moment with what all of this actually looks like from here. Somewhere above you tonight, if you're far enough south to see it, or if you simply know where to look, Alpha Centauri is sitting exactly where it's always sat, a single bright point to the naked eye, resolving into 2 only through a telescope, with a 3rd, fainter star hiding nearby that most people never learn to find at all. It doesn't look like any of what we've spent the last few hours walking through. It looks calm. It looks close. It looks, from here, like an invitation. That's not a false impression exactly. It's just an incomplete one, the way most things visible from a great distance are incomplete. The light reaching your eyes tonight left those 3 stars over 4 years ago, carrying no information at all about flares or tidal locking or a companion star's gravity quietly working against a planet that never quite got the chance to form. It's just light, old, patient, indifferent to everything we've since learned about where it came from. You don't have to hold all of it at once to understand what tonight was really about. A habitable zone is real and calculated correctly, and still isn't a promise. A planet can sit in exactly the right place and still lose almost everything that mattered to a star too young and too violent to leave it alone. A system can look, from a distance, like the best possible chance nearby, and still, on closer inspection, turn out to be a place where 3 separate kinds of bad luck happen to land on 3 separate worlds. None of that makes the sky above you less worth looking at. If anything, it asks something more honest of you than wonder alone would. Not awe at what might be out there, but a kind of respect for how specific, how narrow, how easily disrupted the conditions actually are that let a place like Earth exist the way it does. Somewhere, probably not around these 3 particular stars, but somewhere, the conditions may have lined up differently. We don't know yet. Nobody does. A small telescope with a flower-shaped mirror hasn't launched. A space telescope built for other purposes entirely is still quietly checking a candidate signal from 2021 that no one has been able to confirm or rule out. The question stays open, the way most real questions in this field stay open for far longer than anyone would like. For tonight, that's where we'll leave it. Not with an answer. With 3 stars, close enough to feel like neighbors, distant enough to keep almost everything about them a mystery, still burning exactly the way they were burning before any of us learned to ask what was wrong with the world circling them. Somewhere above you tonight, those 3 stars are still burning, whether you're watching or not. Sleep well,